Hello everyone, we are from Group 8. I would like to introduce my group member. The first one is QING. The second one is NURIRDINA. The third one is NADHIRAH. And the last one is me, SYABILA. So our project title is Stability and Consolidation Analysis of an Embankment on a Clay Layer. So I will move to the introduction of the project. Embankments are widely used in civil engineering projects such as highways, railways, and flood protection structures. They are often constructed over soft clay layers due to land constraints and economic considerations. However, soft clay soils are characterized by low shear strength, high compressibility, and low permeability, which can lead to stability problems and long-term settlements. When embankment loading is applied, the clay foundation may be unable to sustain the imposed stress, causing slope instability and excess pore water pressure. Due to the low permeability of clay, consolidation settlement occurs over time and may affect the safety and serviceability of the embankments. Conventional analytical methods are limited in capturing these behaviors. The objective of this project is to stimulate the embankment's geometry and boundaries conditions using Plexis 2D. Second one is to define the soil stratigraphy and materials properties. The third one is to perform stage construction analysis including stability and consolidation. And the last one is to analyze key results such as deformation, factor of safety, slip surface development, and settlement magnitude.
First, I will talk about our model. We designed an embankment that is 5 meters high with a 1 vertical to 3 horizontal slope. Under the embankment, there are 3 different layers of clay. The first layer is natural clay, followed by silty clay and stiff clay. The total depth of the soil is 18 meters. This model helps us see how the embankment sits on the soft ground. Next, let's look at the soil properties. We use the cooler models for all materials. We enter data like unit weight, Young modulus, and cohesion for each layer. This value tells us how strong or soft the clay is. We also include the permeability, which is very important for calculating how water leaves the soil over time. Lastly, the water level is set at 2 meters deep. We use stage construction for consolidation analysis and calculation. In phase 1, we build 3-meter layers of embankment in 5 days. Then in phase 2, we wait for 10 days to let the soil consolidate. We repeat this in phase 3 and 4 for the final 2 meters. This waiting time is key because it lets the soil get stronger before we add more weight. In the final step, phase 5, we add a traffic load of 23 kN per meter on top of embankment to make sure the design is safe. We add safety phase after every construction step. This phase calculates the factor of safety.
From the deformation results, the deformed mesh and total displacement contours show that the maximum settlement occurs beneath the center of the embankment and decreases towards the sides. This indicates that the applied embankment load is mainly transferred to the underlying clay foundations. For the stability results, the safety analysis shows a rotational failure mechanism developing through the soft clay layer with the slip surface passing beneath the embankment toe. The factor of safety varies with construction stages and is lowest during early loading, confirming that stability is most critical during constructions. Finally, the consolidation results show a clear relationship between settlement time and pore pressure dissipation. The settlement time graph indicates rapid settlement during embankment loading, followed by slower consolidation settlement. The excess pore water pressure increases during construction and gradually dissipates with time, confirming time-dependent consolidation behavior of the clay foundations. From the stability analysis, the results show that the embankment remains stable, but the critical failure mechanism develops as a rotational slip surface through the soft clay foundation. This indicates that embankment stability is mainly controlled by the shear strength of the underlying clay rather than the embankment field. The lowest factor of safety occurs during the early construction stages due to high excess pore water pressure, while stability improves after consolidations. In terms of settlement, significant vertical deformation occurs beneath the center of the embankment. This is caused by the high compressibility and low permeability of the clay layers, which result in both immediate and long-term consolidation settlement. Overall, the short-term behavior is dominated by reduced effective stress and lower stability during construction, while the long-term behavior shows improved stability but increased cumulative settlement. Therefore, stage construction with sufficient consolidation time is essential to ensure both safety and long-term performance of the embankment.
In conclusion, this project successfully analyzed the stability and consolidation behavior of an embankment constructed on clay foundation using Plexis 2D. The results show that the embankment is most critical during early stages of construction due to high excess pore water pressure and low effective stress in the clay. However, as consolidation occurs, pore pressure dissipates and the factor of safety increases, indicating improved stability over time. The results show that significant settlement was observed, mainly influenced by the high compressibility of the clay layers, with settlement continuing in long term. Overall, the embankment performed satisfactorily when the stage construction and adequate consolidation periods are applied, highlighting the importance of considering both stability and long-term settlement in embankment design on clay soils.